So this is note 7, the end of page 4 and page 5. This is a really important patterns that you need to get if you're going to simplify radicals with some facility. So we're going to assume x is positive. Now, we just learned that, hey, if you take the square root of x squared, the best you can say that's the absolute value of x. But if x is positive, that's just going to be x. Just remember, the absolute value of a positive number is just its number. You don't need the absolute value of bars. It doesn't change a thing. So as long as x is positive, the absolute value of x squared is just x. Now, what do you think the square root of x to the 4th is? Well, remember, I'm asking, what is it that you can square that will give you x to the 4th? Well, if you square x squared, that will give you the x to the 4th. So the square root of x to the 4th is x squared. Since x squared squared, I just did not leave enough space, is x to the 4th. What's the square root of x to the 10th? Well, I'm asking, this is what I'm asking, what do you have to square to get x to the 10th? Well, power to a power you multiply, that would have to be x to the 5th. So the square root of x to the 10th is x to the 5th. Now, look at what the square root is doing to the exponents. Square root of x to the 4th is x squared. Square root of x to the 10th is x to the 5th. It looks like the square root divides an exponent by 2. Okay? That's the pattern. And let's note, the index for a square root is 2, but it's so common we just drop it. So if there's no index, it's understood to be 2. So that index is dividing into that exponent. Okay, now, a perfect square would be a number that when you take the square root, you have no radical left over. So x to the 10th is a perfect square. X to the 4th is a perfect square. We know that for variables, the square root is going to divide the exponent by 2. So for a variable to be a perfect square, what kind of exponent would it need to have? Well, something divisible by 2, so it needs to be an even exponent. So this is really important. You can look at variable expressions and just say, hey, that's got an even exponent. That means it's a perfect square. I could take the square root easy peasy. Really important. So let's look at just a quick problem here. Square root of x to the 6th. Hey, is x to the 6th a perfect square? Yes, it is. It has an even exponent. And what's the square root of x to the 6th? Well, remember the index is 2. You just divide that index into the exponent, you get x to the 3rd. Square root of x to the 16th. Is that a perfect square? Yes, it is, because that's an even exponent. And the square root will just cut that exponent in half. That's x to the 8th. Be careful with this one. 16 is not an exponent. Sixteen is just a base. The square root of 16 is 4. So some people overuse this rule working with the exponents. All right, so there's your pattern for square roots. So on page 5, we do something similar with cube roots. So what's the cube root of x cubed? Well, that'll be x. Right? What's the cube root of x to the 6th? Well, this is asking what can I cube to get x to the 6th? Well, power to a power you multiply, so that would be x squared. What's the cube root of x to the 9th? Well, if I cube x to the 3rd, I get x to the 9th, and that's what the cube root is asking for. What is it that I can cube that will get me back to the x to the 9th? So that's x cubed. So What's the pattern here? Well, it looks like all the exponents are being divided by 3. And in fact, that is the pattern. A cube root divides an exponent, not a base, but an exponent by 3. Now, all of these variables are perfect cubes because when I took the cube root, I don't have a radical left in my answer. So for a variable to be a perfect cube, so that is to have no radical left in the answer, what kind of exponent would it have to have? Well, it would need to have an exponent that is divisible by 3. If you want, you can say a multiple of 3. Saying the same thing. So that's an incredibly important pattern to remember. So if I ask you to simplify the cube root of x to the 27th, is x to the 27th a perfect cube? Yeah, because 27 is divisible by 3. In fact, that's what the cube root will do. That's just going to be x to the 9th. But again, be careful. The cube root of 27 is not an exponent, that's a base. That's just 3. Okay, now here's another handy dandy little fact. Cube root of x squared. Can I simplify that? Well, 1, 2 is not a multiple of 3, so this is not a perfect cube. But also, the exponent is smaller than the index. So in most cases, in all the cases I'm going to put in your homework, if that happens, where the exponent is smaller than the index, we really can't simplify. We can change forms. We'll learn how to change forms for that, but we really can't simplify that. All right? So here's the pattern for perfect cubes. Exponent needs to be a multiple of 3. Now let's look at fourth roots. Well, what's the fourth root of x to the 4th? Now, that would be the absolute value of x if we didn't assume x was positive, but at the outset we decided to assume x was positive, so we can just say that's x. What's the fourth root of x to the 8th? So this is asking, what can I raise to the 4th power to get x to the 8th? I know my exponential rules, power to a power I multiply, so that would need to be an x squared. What's the fourth root of x to the 12th? Well, again, this is asking, what can I raise to the 4th power to get x to the 12th? Well, that would be x to the 3rd, because power to a power, you multiply exponents. So, what's the pattern? The fourth root is dividing the exponent by 4. And then how do you tell if a variable is going to be a perfect fourth? That is, the answer will come out without any radical? Well, since the fourth root is going to divide the exponent by 4, we need to have an exponent that is divisible by 4. Or a multiple of 4. Whichever way you want to think about it. So, fourth root of x to the 20th. Is x to the 20th going to be a perfect fourth? Which is a very different thing in music than it is in math. The answer is yes, because 20 is divisible by 4, and that's exactly what I'll do. This is going to be x to the 5th. But what if you had to simplify fourth root of x to the 3rd? You'd say, no can do. 3 is definitely not divisible by 4. In fact, the 3 is smaller than the 4. So we would call that already simplified. We're going to learn to change forms here, which is not really simplifying, it's just changing forms. All right. Now, there is an overarching pattern. I don't want to do 5th roots, 6th roots, 7th root, 8th roots. There's an overarching pattern. Didn't we always take the index and divide it into the exponent? The index divided into the exponent. So that's the pattern. The index of the radical divides into the exponent. And so there's just one thought you have to remember, is this one. So, and then if you want to know if a variable is a perfect root, its exponent must be divisible by a multiple I said this differently. The exponent must be a multiple, I went with that, of the index. I was about to say the exponent must be divisible by the index. That's another way to say it. So we didn't talk about fifth roots, but you can do this now. Is the exponent divisible by 5? Oh, it sure is. So just do that. That's going to be x to the 6th. Okay, we could do 6th root of 12. Is the exponent divisible by the index? Yes, it is. So that's just going to be x to the 12. Did I say x to the 12? I meant x squared. It must be too late at night. So these patterns are going to help us when we start simplifying more complicated radicals. So, and this is the overarching pattern. So remember, the index divides into the exponent, and for something to be a perfect fourth or a perfect fifth, or basically to simplify so that the answer does not have a radical, that exponent needs to be divisible by the index.